single flame can light a million more.
Okay, so what I'm doing is I'm gonna, what they do call a hot pot test on this capacitor. So before I go and I hit it with the full 10 amps worth of current that plate transformer can put out, I want to slowly run the voltage up on that cap, that big gray thing in there, which is a 22,000 volt capacitor that holds 100 UF worth of capacitance. Now we're all very familiar with the rule that if you've got a 22, let's say a 10,000 volt cap, and you only run it at 3,000 volts, the capacitor only has 30% worth of its circuit available for storage, so therefore you're not getting the full UF capacitance rating out of the cap. I'm going to charge this to, well, when I'm said and done with it up on a 20, I'm going to be somewhere in the area of 12,000 volts. But instead of being down at like 15 UF, I'm still going to have 60 UF worth of capacitance left that I'm going to be using out of the capacitor. So that's a lot of scoochum storage. So I've got the bleeders inside the box, which are the big 20K OR mics, which I have 8 of them in there, all in series as my bleeders. And they're 300 watt OR mics, by the way, like 1.5 inches across, a good 12 inches long or better. Now I got my 10-to-1 reduction probe stuffed in there. Now what I've got over here is what they call a smart Transensco neon sign transformer, which will go to about 9,000 volts, but it's only able to produce 30 milliamps worth of current. 9,000 volt transformer, not the most dangerous thing in the equation. That gray capacitor is like a bomb. It's instant amperage, instant current right now. Now, believe it or not, I'm going to stand about 8 feet away from this thing as I run it up for the first time. And what I'm wanting to prove to myself is that there's no shorts inside the plates inside the cap. Now, since I've had this thing sitting here, just with the leads hooked up, and there's no bleeder, and the reason I can't have a bleeder circuit engaged, and that's what makes this very dangerous, is, well, the neon sign transformer only puts out 30 milliamps worth of current. The big OR mic bleeders that I have built in this cabinet can dissipate more energy than what the sign transformer can put out. So I have to pull that out of circuit. Well, the other thing is this capacitor is so big that the neon sign transformer can't handle the inrush current. Okay? So I got to slowly stack the voltage in there. Now I'm also going to stand back and control this thing with the variac. So you're going to hear me twisting a knob, and that's me turning the variac up. So, because it's a smart transformer, it doesn't turn on until there's almost 5,000 volts worth of output current, which I don't like, but when I went to go get the neon transformer, the only other one they had looked like it came out of Grandma Annie's attic, and it was all rusted, and I was very worried that one of the phases might go open to ground. Then we have all kinds of problems. This is my bridge rectifier ring that's just hanging out in free space. I've got the 2 little 100 ohm resistors in there as a glitch shock back resistor, so if something fails inside these diodes, those resistors are going to go boom, which will protect us from the capacitor. Now over here to our right, this is a direct lead off that cap. Even my arm fully extended, there's still about 2.5 feet worth of space. Now what I've also got attached to the bleeder bar is this little mess. This is 15,000 volt high volt wire attached to an almost a 6 or 8 foot long piece of pure virgin Teflon that I use as what I wrap my plate chokes and stuff against. There's still 500 volts present on the cap just from it sitting here in the air. Just the air, the electrons moving around it are charging the cap. This is my last major test. After this, I'm going to start doing full up stuff with this box. So let's go over here and let's take a quick look. Now this is about the most dangerous thing I've ever done on video. I will be wearing my safety glasses because I had a guy comment on that. Don't worry, the safety police are in full motion here. Now we're going to zoom down in on the cheap, shitty, straight from China freight voltmeter because I don't honestly give a fuck about it. If I burn it up, what's 20 bucks where my fluke's like $250. So for every volt we see, as we all know, I've got a 10-to-1 reduction probe. So those guys that don't know how this works, every volt that's present in this section past the decimal point equals 1,000. We're going to go way up on that. These are in hundreds. So 400, and there's 460 volts sitting static in the cap right now at this moment. Let's put on our personal protection gear, which involves a cup. Our earmuffs, because if any of this goes to ground, it's going to go bang. And our safety glasses to keep our virginal eyes free of debris. I don't feel like having to go get a drill put in my eye to dig out a piece of fucking shrapnel from this goddamn bomb I've built. Okay, here we go. Turn on the variac. 3, 30, 40, 60. Transformer coming on. Transformer's putting out volts. It's 1,000 volts. 2,000 volts. 3,000 volts. 4,000 volts. Now I just got the transformer base idling. So this is slowly charge up somewhere in the area of about 5,000 volts. That's why I checked the transformer came on at here just a minute ago. Now at any point, if the voltage comes to a complete sudden stop, that tells me we've got a short in the plate. Now what we're going to do is when this stops, it should stop somewhere about $6 grand. Because if I'm putting 5,000 in it, post-rectified, that would be 1.145. It's going to be somewhere in the area of $6 grand. 62, 6,300. We're going to take the voltage off the cap and sit here and watch it statically now that we've charged it halfway. Okay, we've kind of leveled out now. The transformer's off, and we're just looking at the capacitor's ability to hold 6,000 volts worth of current. Now we're going to be losing a little bit because the air, yes, the air is moving in here. So 6,350 volts. 6,340. So we don't have a hard leak between the plates. It's 6,000 volts. Let's go ahead and start filling the bucket up again. Going on up. 7,000. 8,000. So shit starts to get real spooky, folks. $9,000 volts. I officially have 3 times more current stored in that capacitor than what's in an SP220. Now as we're slowly counting up, I've got a little bit more to give it on the Variac. What I'm looking for is any kind of little step leads or anything starting to arc or any kind of spacing issue inside the cabinet. Now all the circuitry is disconnected from, completely disconnected from the cap. But I want to make sure all the other components that are around it are adequately spaced. There's 10,000 volts at 100 UF. So your little taser that you got, the little taser, right? It runs off a 9-volt battery. Runs at about 10,000 volts. There's almost no amperage behind that. This is enough to blow part of my arm off, probably pretty much in half, and kill me in the process. So it's not only a painful way to die, it's a violent, ugly way to die. But at least the wounds will be cauterized. There won't be a bunch of blood, but there'll be hunks of little flesh to pick off the ceiling. Okay, we've come to an idle at almost 7,000 or 11,000 volts now. Just going to sit here and do its thing. It's 2,000 volts higher than what you can put onto a 3,000 tube. 11,000 volts. So we're only 1,000 volts away from where I'm going to operate this thing on a 20. Remember, we're only at half the capacitor's rated value. Ugh, that's scary. Just because I know what can happen to me. Okay, let me scooch the Variac up here a little bit. We're going to continue to climb. Variac is tapped out. We're putting 130 volts in, so we're going to get roughly 9,000 volts worth of charge potential out of the smart transformer. So let's do the math here real quick, guys. 9,000 times 1.45. We should top out around 13,000, somewhere in there. If the circuit's 100% efficient. Remember, we've got that 50 ohm resistor in there. There's air moving inside the room. So when I take the voltage off, you got to expect to see a little bit of leakage coming off the transformer as the electrons free roam and step off into the atmosphere. Ionization, basically. And you'll see that in 10 volt intervals at this stage of metering. That's after we take the voltage off. So we're climbing up slowly. Ever tell you guys what my second job out of line college was when I wanted to be a power lineman? I did helicopter hot line insulation replacement. So it'd sit on the side of the skid, and we would change out the spacers on 200, 300, and 500 kVA lines. So what I'm going to show you next, it's not second nature, but I'm fairly comfortable with what we're going to do next. It's going to be cool. It's going to put on a nifty, neat little light show for everybody, but it's not at all really dangerous, taking into account the load of resistance that is sitting on the other side of these two terminals. So we've topped out roughly, and we can sit here and slowly let this cap charge up. The transformer doesn't have enough oomph to carry it forward anymore with that 50 ohm glitch resistor in there, which is a substantial amount above the actual circuit's potential when you're talking with a 30 milliamp transformer. I'm only operating this transformer with about 15 milliamp worth of current. Most glitch resistors operate, you guys, just so you know, anywhere on the 10 to 20 ohm range, and they're usually within, well, the smaller boxes you can get away with a lower wattage rating of like maybe 35, 40 watts, but the bigger boxes you got to have like a 300 watt resistor or 200 watt resistor in there. See, it's slowly counting up. And that's because of this right here. This resistor right here. I'd show you on the FLIR, but that's currently about 112, 113 degrees. I'm not putting my arm anywhere out in that space to measure that and get it in frame. So you guys are just going to have to take my word for it. When it comes to high voltage, the only insulator is space or flat surface area. See, we're slowly counting up. Very slowly counting up. It'll keep going. It'll count up to about 1,300 or so. So these two little red wires here, the alligator clips, which are basically like fuses, there's 9,000 volts between the two of those. 9 grand. Between these two wires coming off the rectifier, there's 12,500 volts worth of current. Well, 12,500 volts worth of voltage. And about 50 UF worth of capacitance, which is enough to kill you, deader than dead. Let's go back over here. Let's zoom in on this puppy real quick. Okay, we're at 12,500. We're going to cut the neon transformer off now. I know I'm good to 12,500, as far as the capacitor doesn't have any leaks across it. So the capacitor is not going to break down, I know for a fact, up to 12,500 volts. Okay, I just shut the transformer off. We're going to slowly start our walk back down. It'll get down below about 5,000 volts and it'll just sit there. And it'll just sit there. And if it's not acted by another outside source, because we've gone to the point at that voltage range where the atmosphere, depending on the moisture in the atmosphere and all the other little particulates that are in the air that's surrounding the terminals on the capacitor, can no longer conduct any kind of current a couple electrons at a time. That's why you always ground out your high volt caps if they're not in use. Because you go to pick that up, the capacitor is still storing all of the current inside of it on the plates. With this slow of a step down, that cap is in good shape. And that thing's about the size of 4 car batteries. Let's go over here for a minute. Are you going to focus? Focus. Focus. There we go. Now we're going to start letting the lightning out of the bottle. I'm going to pick up this rod and I'm going to bring the bleeders into it. So there's 12,180 volts worth of voltage inside of that cap at about 50 UF, 60 UF, somewhere in there. We're going to start letting go of some of these free roam electrons. Just in case you missed that, I want you to see how far this, oh, smell the ozone, how far this can conduct at this distance. You see that? That's at 9,000 volts. We've lost 3,000 volts worth of current, or 3,000 volts worth of voltage and about 25% of the storage capacity. So look at that. This is why you want to keep your arms and your hands and everything you got out of the inside of your box. You don't ever want to touch it unless you know what you're working with. It's like a dragon. It's going to lay there sleeping, patiently waiting to kill you, only for you to be dumb enough to put your hands in a space or proximity to where it can do just that. It's trying to find its way back to ground. It's trying to always close the circuit. It's trying to always go back to ground. Now, with all that arcing and sparking that we've had going on, how much current do you think we've lost, or how much voltage do you think we've lost? There's a lot of energy stored inside of that cap. A lot of energy. Unless you know what you're doing, don't play with the devil. Okay, I want you to see something. I stopped here for a reason. That's the same amount of voltage that's inside an SP220. Or a Drake. Or about 2/3 of the way up on a 3000. A little bit higher than that's a 1500. We're talking about tubes. A little tiny arc is enough to take you to go see the angels. This is so dangerous. I cannot stress this enough. Don't ever, ever, ever try this at home. If I wasn't comfortable working with these high voltages from my 2 previous careers in electrical field, don't ever, ever, ever try this at home. Now I've just turned the transformer on. We're going to slowly let this charge up, and then we're going to bleed the thing down to 0, and I'm going to move on with my night. Then I'm going to go in and kiss my wife and tell her I love her very much, because I'm one step closer to getting this big giant bastard running. The main reason I had to do this, and I just thought I'd video, the main reason I had to do these tests is because I don't know. I bought this capacitor used, and it's been sitting here for a year waiting for me to install it. And I wanted to test its ability to hold current, how high I could go with it, what the plates were like on the inside of the cap, and it's told me everything I need to know. The only thing I didn't show you is the grid meter I got going on this side of the thing to watch the amount of amperage that the transformer's pulling. So we're not going to take an hour and let it charge up that extra 100 volts because we're going to burn it off in the first second of arcing, so, or extra 1,000 volts, I mean. Gentlemen, my name is BBI. And without a shadow of a doubt, I am the biggest mud duck in Idaho. Come check us out, www.bbiamps.com. You can find me on Facebook, Twitter, Snapchat, Instagram, and of course where you're watching me today. I don't get to be here without all you guys, and I don't get to show you all this cool stuff without everybody's support. Gentlemen, be fearful of high voltage. It will kill you deader than fuck. And that ain't no joke. We'll see you. Bye.